Review of the first half of Chapter 2, 2.1 to 2.3. Let's get started here. 2.1 was on patterns and inductive reasoning. We are asked to describe the pattern for each sequence and then find the next two terms. So let's look at the first one. We go from 12 to 17 to 22 to 27 to 32. To me, it looks like if we add 5 to the previous term, we get the next term. So 32 plus 5 is 37, and 37 plus 5 is 42. That looks like it fits our pattern nicely. Next one, we go from 5,000 to 1,000 to 2,000 to 40. We're getting smaller, so it's either subtraction or division. I'm going to go with dividing by 5. So if I divide 40 by 5, I get 8, and if I divide 8 by 5, I get 8/5, and I see no reason why we shouldn't just leave that as an improper fraction. There's no harm there. All right. Next, we are finding a counterexample to show that each conjecture is false. So the result of a number multiplied by a positive integer is always larger than the original number. So we're going to multiply. I am going to choose 3 as my positive integer. And let's see, we could go 2 times 3 is 6. Well, 6 is greater than 2. But we can't forget about the negative numbers. Negative 2 times 3 equals a negative 6, and negative 6 is definitely not larger than negative 2. So there's our counterexample. A four-sided figure with 4 right angles is a square. Well, a square does have 4 sides and 4 right angles, but so does our good friend, the rectangle. Right? So, counterexample. An animal is green, it is a frog. Well, you know what? There are other green animals. We have a little green lizard. Draw a little lizard here. Our little lizard friend. His tail sticking out there. Kind of a funny looking lizard. He's still green even if he's a funny looking lizard. We could fix his tail. Oh, well, now fix the other side of his body. There's more of a lizard. And we could also do our friend, the turtle. Give him a little tail. He's our long-necked turtle. Make his pretty shell pretty. Alright, that's just a waste of time. But it was fun. So, green animals, turtles, and lizards. Good counterexamples there. And our last one, any 3 segments form a triangle. Well, while that is true, it is not always true, because I can take 3 segments and form a baby T, or the Japanese hi. Fun stuff. 2.2, conditional statements. We are given a statement. We want to identify the hypothesis and conclusion, then write the conditional and all of its minions, so the converse, the inverse, and the contrapositive. And then we are to determine the truth value of each one of those, and if it's false, give a counterexample. So lots of good stuff going on here. So let's do the first one. Residents of Miami live in Florida. So let's split it up into our 2 ideas. You're a resident of Miami and you live in Florida. Our hypothesis and our conclusion, like we were asked to identify. And so let's get started. Lots of writing here. Write our conditional. Our conditional is our if-then statement. So, if you are a resident of Miami, looks like the speed this video goes is how fast I can write. Then you live in Florida. Is that true? If we're living in Miami, we are living in Florida. That's true. Now our converse. Remember our converse, we switch. So if you live in Florida, then you are a resident of Miami. Is that true? So we're living in Florida. Are we a resident of Miami? We could be, but what about Tampa Bay? What about Orlando, Pensacola, and so many other cities that I can't think of right now? Tons of cities in Florida. All right, let's now write our inverse. Our inverse is where we negate our conditional. So if you are not a resident of Miami, then you do not live in Florida. Is that true or false? We are not living in Miami, so we're not in Florida. Well, we expect that one to be false for the same reason above. Tampa Bay, Orlando, Pensacola, all of those good places. This is not a surprise because we know our converse and inverse are equivalent statements. So we expected them both to be false. Once the converse was false, we expect the inverse to be false. And our contrapositive. Contrapositive is where we negate our converse. So if you do not live in Florida, then you are not a resident of Miami. True or false? We're not living in Florida, so there's no way we can be a resident of Miami. It was expected as well because our conditional and our contrapositive should be equivalent statements. Right, next one. Measures of two complementary angles summed in 90 degrees. We need to figure out our two statements here. So complementary angles is our hypothesis, and the measures summed to 90 degrees is our conclusion. So let's get to this. Write our conditional. If two angles are complementary, I'm going to shorten here just in the interest of time, then the measures add to 90 degrees. That is true. We know complementary angles add up to 90 degrees, always. Converse, switch it around. If the measure of two angles add up to 90 degrees, then they are complementary. We know that is true as well. Two angles, if the measures add up to 90 degrees, you have complementary angles. Inverse, remember when we negate our conditional. So if two angles are not complementary, then the measures do not add to 90 degrees. Is that true? If you're not complementary, then when we add the measures, nope, they're not going to be 90 degrees. So that is true. No surprise there because our converse and our inverse are equivalent statements. Our converse was true, so we expected our inverse to be true. And our last one here, contrapositive. Remember, we negate our converse on this one. So if the measure of two angles do not sum to 90 degrees, then they are not complementary. Is that true? So the measures of our angles are not adding up to 90. That means we are not complementary. Again, not a surprise there. 1, because conditional and contrapositive are equivalent statements, and 2, we know the definition of complementary is the measures sum to 90 degrees. So no big surprise on that one. All right, let's go on to 2.3. Biconditionals and definitions. We are to write the conditional and the converse, and if they are true, write them as a biconditional. So let's start. Let's break it up here. Vertical angles are congruent. Our two ideas are vertical angles and congruent. Let's write a conditional. Our conditional would be if angles are vertical, then they are congruent. Is that true? Yes, it is. We know that vertical angles are congruent. So now let's write a converse. So we switch it around. If angles are congruent, then they are vertical angles. True? Well, we know that vertical angles are formed when lines intersect. So we have these also top to bottom. So we've got our vertical angles are congruent. Is there any way to draw congruent angles that are not vertical? How about these guys here? How about our angle bisector? So that's false. If we bisect an angle, we have two congruent angles, and they are not vertical angles. So that one is false. Not a good definition. Here shortly we're going to get our vertical angles theorem, and you will get your good definition for vertical angles. All right, perpendicular lines intersect at a right angle. So perpendicular lines and intersecting at a right angle. Let's write our conditional. If lines are perpendicular, then they intersect at a right angle. Is that true? Yes, it is. Perpendicular lines form a right angle. Converse, switch it around. If lines intersect at a right angle, then they are perpendicular. Is that true? Yes, if we have two lines and we draw a right angle there, then we call them perpendicular, so that's true. So now we can write both our conditional and our converse are true, so we can write a biconditional. So what are we trying to define here? I think perpendicular is what we are trying to define. So remember, no if then. This is just lines are perpendicular, and then we connect them with if and only if they intersect at a right angle. And if you remember, that's the definition of perpendicular, isn't it? Perpendicular is lines that intersect at a right angle. Perpendicular lines intersect at a right angle. So that was a good one. All right, and the last one here, parallelogram is a quadrilateral. You should go, hey, we have seen this one a million times. Come on, change colors. Parallelogram and quadrilateral. Our conditional says if a figure is a parallelogram, those two lines mean parallel. We're going to see that a lot in Chapter 3. That's going to be everything to us in Chapter 3. So if a figure is a parallelogram, then it is a quadrilateral. Is that true? Yes, we have talked about this a lot. Parallelograms are quadrilaterals. And our converse, if a figure is a quadrilateral, then it is a parallelogram. And you should have seen this coming. That is false, because we have a ton of quadrilaterals. Our rectangle, our square, our rhombus, our trapezoid, kite, any random four-sided figure. Some of these are parallelograms. Rectangle's a parallelogram. Square is a parallelogram. Rhombus is a parallelogram. This is not trapezoid, kite. Those are not parallelograms. So there are counter examples for that. So that would not make a good definition either. When we get to the chapter on classifying quadrilaterals, you'll get a good definition for parallelogram. All right. Well, we don't need that. Write two statements that form each biconditional. So we are now just splitting up our biconditional into its conditional and converse. So we take our if and only if, and then we have our two statements. So polygon is a triangle and has exactly three sides. So the first one, we go forward. We add our if and then. If a polygon is a triangle, then it has exactly three sides. True? That is true. And then we start from the back side and go the other way. So if a polygon, right, because we're talking about a polygon, has exactly three sides, right, sometimes we have to add words in to make nice sentences, then it is a triangle. So if a polygon has exactly three sides, is it a triangle? Yes, it is. Those are true. So this is a good definition for triangle. A polygon with exactly three sides. Shouldn't be any surprise there. All right, an angle is a right angle if and only if it measures 90 degrees. So if an angle is a right angle, then it measures 90 degrees. Well, that's true. And the converse, if an angle measures 90 degrees, then it is a right angle. And that's true, and we know that's true. You should have seen that one coming. We know that the definition of right angle is an angle that measures 90 degrees. So no big surprises there. All right. I got a little typo going on here. So we could put in an if and only if right there. So two rays are opposite rays if and only if they share the same endpoint. So if two rays are opposite rays, then they share the same endpoint. Is that true? No. What do opposite rays look like? We know that opposite rays make a line and share an endpoint. So that statement is true. Let's write the converse. Switch it around. If two rays, because we're still talking about two rays here, share the same endpoint, then they are opposite rays. Is that true? Well, can we draw any rays that share an endpoint but that are not opposite rays? I am going to say yes, we can. Any angle that is not a straight angle is made up of rays that share the same endpoint. So that one is false. Oh, and the end here, the last two problems. We are doing good definition. So we have three criteria for good definition. They use common terms, they are precise, and they are reversible, right? Biconditional. We can write an if and only if statement out of them. So let's look at what we have here. An acute angle has a small measure. Well, let's start out. Is it common terms? Yeah, that's got common terms. Those are things we all know. What about precise? You should have seen that as soon as we read it. No. Small is not a precise term in any way. So what would we have done instead? We would have done our 0 to 90 degrees, right? 0 is less than x is less than 90. So it's already not a good definition, but we could check, is it reversible? So we would go, if your angle is acute, then small, I can barely even say it, small measure, that would be true if we made this the 0 to 90, right? So if small measure, I still have a hard time doing that. If it was the 0 to 90 measure, then acute. So this has potential, both of those are true. A 0 to 90 measure would be acute. This has potential to be a definition, but this precision problem, it's just not even in the running. So if we fix the precision problem, we could have a good definition here. All right, let's try the last problem here and be done with this. Squares have 4 congruent sides and 4 congruent angles. Common terms? I know that y'all might want to argue with me that congruent is not a common term that everyone uses, but you are in geometry. Congruent is possibly the most common term you are going to use. So we are going to call that common terms. Is it precise? Most definitely. Square is a very precise type of figure. 4 congruent sides, 4 congruent angles, good precision there. Let's check if it's reversible. So if we have a square, then 4 congruent sides, 4 and 4 congruent angles. And we switch that around. If 4 congruent sides and 4 congruent angles, then you're a square. Squares, if you're a square, that one's true. And if you have those characteristics, then you're a square. That one is true. This would let us write a very nice biconditional. A figure is a square, and then we would connect it with if and only if it has 4 congruent sides and 4 congruent angles. So that makes a very nice definition. Squares have 4 congruent sides and 4 congruent angles. This one is definitely a good definition. Common terms, precise, and reversible. And that is the first half of chapter 3. As long as you are careful writing your conditionals, your converses, and the other minions, the inverses and contrapositives, you will be fine on these. Just make sure you are using the proper format. Keep your notes handy so that you can refer to them if you need to check your order and check which ones to negate and which ones to switch your hypothesis and conclusion. And I am certain that you will do great on the quiz.